Okay, so we are going to continue with the class. So I already started the recording of the second half of the class. First of all, I hope that you have time to go through the characteristics of some of the processors, just to see that some of the concepts that we have seen so far can be found in the characteristics of these architectures. So just to pick an example, the Zen2 microarchitecture. Microarchitecture is a very popular microarchitecture from AMD, and the second version, Zen2, is from 2019. Okay, and it's actually a very successful architecture because actually with Zen architecture, we can say that this manufacturer, AMD, researched, okay, from the ashes because it was almost irrelevant a few years ago after another period of success. And this architecture is actually a good idea because it has a very good performance, and they, at least in the desktop market, offer a better price or a better product for the price with respect to Intel. Okay, so if you check the characteristics, you are going to find like several concepts that are relevant. For instance, the number of cores configuration. So you can see that this architecture can be implemented in processors with 4, 6, 8, 12, 16, 24, 34, and 64. Okay, depending on the model that you buy. Obviously, for instance, I have one with 12 of, I believe this is this specific architecture, and it costs like 400 euros or something like that. Then in the outline, you can see things that ring a bell for you, probably like superscalar, that is speculative, that it has register renaming, the number of stages, okay, that the pipeline has, that are 19, and then the number of instructions that can be issued at the same time. So in this case, you see that this is 4-way, and this means that we can issue 4 instructions at the same time. Also, in this rightmost part, you can see other things that are relevant, like the type of SC instructions that are supported. When we talk about instruction level parallelism, we mentioned that one of the main sources of hardware to exploit this are multimedia extensions. So for instance, for this processor, you see that they support the original MFEs, all the versions of SSE, that is another family, and then the most modern AVX, not including the most up-to-date, that is AVX 512. Okay, so if you check one of these processors, it's very interesting to see like the different models that you can buy, depending if you have a desktop computer, if you are in the middle between a desktop and a performance computer, or if you are in a supercomputing server. Okay. Also, it's quite interesting the integration technology that is usually expressed in nanometers. Nanometers, the integration technology, the number that they give you is the distance between a pair of transistors. I believe this one is 10 nanometers. No, is 7 nanometers. Okay, this is the integration technology that they use. And actually, I heard that the other day that the new architecture was 5 nanometers. Okay, so the lower in this case, the better. Also, as you are studying some of you HPC tools, normally here they tell you which M-arch flag you have to activate the specific optimizations for this architecture. So for instance, for 7 version 2, you have to put this, okay? And it's going to try to optimize heavily for this architecture. Obviously in Intel, you don't have support for this architecture, okay? Just in GCC and in this case, LLVM. Okay, so you have the characteristics of the functional units, and then you have this monster illustration about the pipeline of a single core. That in this case is very detailed, okay? And you can see here that as it is superscalar, you can identify which components are necessary in order to implement this. Also, I believe that is quite important that you check, for instance, the cache characteristics, how many levels it has, how many levels are private to each core, and how many of them are shared. Okay, I believe that it's usual that they have the level 1 and the level 2 private to each core, and then a big level 3 shared cache. Okay, and I believe this is the case of this one. Okay, and you have other things that are interesting. I already mentioned that one of the most important things for the performance of a processor is the branch prediction unit. Okay, so in order to make a good prediction, you can see that the predictor is quite complicated. Okay, and you can see all the details about how they think it works. Okay, because I don't know if this information is published. Maybe maybe they took it from a patent from AMD, and that's the source of the information. Okay, so obviously these articles have much information, and obviously all of them is not relevant for you. Okay, just I want you that in the task you are able to correlate the information or the concepts that were introduced so far in this course, in this subject, with the concept that you find for the architecture of the supercomputer that you that you work on. Okay. Okay, so let's finish the chapter. We are going to finish just talking about multi-cores. Okay, so just to review the mind map. In the first part of the class, we talk about parallelism inside the chip, and we saw like 2 different sources of parallelism: instruction level parallelism, okay, and we already comment on this part of the mind map, and then in the most recent part, we talk about thread level parallelism. So we have the idea of multi-threading, just multi-threading, which means that we are going to execute several threads at the same time, and we have to switch between one and another, or one and another, okay, depending on the number of threads that we have. And we can do this switching at a finer grain, so this means that we switch every cycle, okay, and there are examples of architectures from this century that are implemented like this, okay, although this is not a very popular idea. And then the other idea is switching on long stalls. So every time you know that you are going to stop for a while because you have a memory access out of the chip, okay, out of the chip of the processor, then you can switch to another thread to make useful things in the meantime. Simultaneous multi-threading is the key technology here, is what you usually are going to find in most modern computers. So it's the ability that each core of a processor has to issue several instructions of different threads at the same time. Okay, this enables out of order, the coexistence of different contexts at the same time. So obviously this complicates a lot the design, but this is the state of the art. Okay, this is where computer architecture is right now. And then we have more special architectures like the CMP and the CNT, okay, that were not so successful, and probably most of the one that you are going to find is going to be like an instruction level, multiple issue, dynamically scheduled superscalar processor with thread level parallelism using simultaneous multithreading. Okay, this is like the state of the art of computer architecture. So what we are going to talk about now are just some design considerations about multi-core processors. Okay, so just review one more time the historical context in which multi-core processors arise. Until the beginning of the 21st century, every new family of processors from Intel, AMD, or whatever, just base the increase in the performance on the increase of the frequency of the processor. This was one of the main sources. Also, the additional transistors were used to complicate the design of a single core, okay? Just making things like branch prediction, trying to do some kind of multithreading, supporting multiple issues, superscalar processors, these kind of things, okay? This was the main motivation of the evolution of the processors. But at some point, the increase of the frequency was not possible anymore, okay? Because as we saw at the beginning of this subject, when you increase frequency, you also increase power consumption. And also you have to dissipate more heat, okay? And if you want to still use a ventilator or even a liquid system, you need to keep this under control. Okay, so increasing the frequency, we can do it, okay? But obviously this is not going to be affordable for the market. So there is a number of problems about that. And if you remember, there was also a pushing element, which was Moore's law. The Moore's law, Gordon Moore, was one of the founders of Intel, and he predicted the evolution of the integration technology that we have just mentioned. Okay, when I say this processor family, this architecture is based on an integration technology of 10 nanometers, I'm telling that the distance between two transistors is 2 nanometers. Okay, so this distance has been decreased for many years, and this allows to increase the density of transistors in the chip. Okay, so the question is, we cannot complicate the design of a single core fast enough. We cannot use that to increase the frequency of the processor. So what do we do with the extra transistors that we can put in the same chip? Okay, and the solution for that was just to make copies of the same thing, okay, at first. So this is the advent of the multi-core area. They decided to put several copies of the same thing in the same chip, okay? Also, another thing for which they use the extra transistors available in a chip is to put more cache memory. Okay, as you already know, the memory hierarchy is a key component of the computer. The well-functioning of this component is very relevant, and one factor for this is that the cache memory is big enough. Okay, so at the beginning, when cache memories appear, they were usually implemented off-chip. This means that they were not part of the chip of the processor. You have the processor and then another component which was the cache memory. Okay, so now obviously the different levels of the cache memory are inside the chip of the processor. And if you go to Wikichip and you check the evolution of any processor family, you will see that something that changed from one moment to another is the number of cache levels until 3. This is the magic number that we have right now, and the size of each level. Okay? And actually, something that you are going to notice is that the first level cache doesn't change, doesn't become bigger in every family. It's usually something like 32 kilobytes. There are some with 64 kilobytes, and there is a reason for that. The bigger the cache memory is, the slower it's going to be, okay? And there is not way to avoid that relationship. And it's extremely important that the first level of the cache works almost at the same speed than the processor. So if you try to make bigger the level 1 cache, what you are going to get is a slowdown of the overall operation of the computer. So if you compare two different generations of the same architecture, what you are going to see are increase in the size of the level 2 and the level 3 cache. Okay, but never, at least for many years, you are going to see an increase in the level 1. Okay, being 32 kilobytes or 64, but normally 32 is like a magic number for that. Okay. Okay, so with more transistors, you see that computer architects complicate the design of the processor, allowing multiple issue, out-of-order execution, speculation in the branch prediction and in low-off operations, etc. But the key idea today is to put several cores on a single die. Okay, so in the rest of these slides, what we are going to see are like different design decisions that the designers of a multi-core processor have to take. Okay, so the first decision is where to connect the cores to each other. Okay, so the current solution is this one. Okay, you usually have a chip where all the cores share the level 3 cache. Okay, maybe in some mobile processors you will find processors that don't have a level 3, so they have just a level 1 and level 2, and the shared level is the level 2, and that's where the connection of the different cores happens. But doing the connection like this requires a substantial redesign. So at the beginning of the multi-core area, this was not the solution that was taken. For instance, in one of the first approaches, in Pentium D, the connection between different processors was off-chip. Okay, so basically you have something like a multiprocessor. Or in the Opteron, it happened through the coherence interconnect. Okay, these approaches are not very efficient, but at the beginning, manufacturers wanted to implement multi-core computers without heavily redesigning the processor itself as a whole. Okay, so in order to shorten the time to market, they decided to do these easy and fast solutions. But obviously, we are not in this time. Multi-cores have been with us for many years, and our current solution is to connect cores at a given level of the cache, and normally level 3. Another important thing is fault tolerance support. As we have a processor where many things are replicated, some of them can fail. And the question is if the failure of one of them is going to invalidate the processor as a whole. Okay, so there is some fault tolerance support. So for instance, sometimes if a core stops working, the system can still work with the remaining cores. Sometimes we can isolate a failure in a cache bank, in a memory controller, in the interconnection system, etc. Okay? Okay, another important thing is that all the cores of a processor have to share only the expensive resources. So for instance, the interface with the main memory, with the RAM memory, is shared among all the cores. Okay, the coherence interface, and this is the topic that is being covered by Juan Toriño in the next classes, is shared among all the cores, and the interface with the I/O system is shared among all the cores. This table contains some architecture. These architectures have to be between 1995 and 2005, I believe, more or less. So you can see the name of the processor. All of them are multi-core processors. The number of cores per chip. If they supported multi-threading, and if it was supported, how many concurrent threads could be executed, and the resources that were shared among different cores. Okay, so for instance, in IBM Power 4 and Power 5, this is a very popular architecture, and this is like very paradigmatic of a multi-core architecture. What they share is the system interface, obviously the interconnection with the rest of the computer, and any level of the cache. Sometimes it's just level 3, and sometimes it's level 2 and level 3. In Niagara, they share everything. Okay, and we already talked about this approach. Every resource is shared among different cores. In Pentium D, they share the core because there is a core and nothing else. And the Opteron just share the system interface. Everything else is private to each core. Okay, another another difference, which is key for understanding different products that you have in the market, is to find a balance or a trade-off between core complexity versus number of cores. So when you make a multi-core computer or processor, you can think, okay, I'm going to design a single core, which is complicated and is fast, okay, and it can execute a single task as fast as possible, and then I'm going to put as many of them on the same die as I can, okay? So this was the original approach of Intel Core 2 Duo, okay? That was the original multi-core computer processor from Intel, the first AMD Phenom X4, the UltraSparse 4, etc. Okay, but there is, and actually most of the modern computers are built like this. Okay, I have a core which is superscalar, which supports speculation, simultaneous multi-threading, everything that you can put in a core from an architectural point of view. And then you try to fit as many of these cores as you can in the same processor, in the same chip. okay? But there is another approach, and it's be more aggressive in the replication, in the total number of cores, but with simpler cores, okay? And this is the approach followed by the architecture San Niagara or Tile 64, okay? Actually, for instance, when A&D became very important at the beginning, it was very shocking that Intel i7, the desktop computer, had 4 cores, and A&D was already selling 6 or 8 or something like that. Okay, so everybody thought, okay, they are giving more for less or for the same price, and that was one of the reasons why they succeeded. And obviously, at the beginning, they found a better trade-off between complexity of each core and the number of cores that they put in the same chip. Okay, another approach that is not very popular nowadays, but there are some manufacturers that for many years, this is like a rumor that is appearing from 10 years ago, that they are going to make heterogeneous chips, okay? And I believe that there are some samples in the latest Intel architectures. And the idea is that not all the cores are going to be equally capable, okay? So for instance, I'm going to have 2 of them which are complete cores, very fast with the full package of capabilities. And then I'm going to have like an array of 8 or 10 or 12, which are dumbbells cores, okay? That they are not so good at doing general purpose things, but maybe making matrix multiplications, for instance, they are very fast. There was an attempt of this many years ago. Do you remember the cell processor? Cell processor? I always remember the cell processor, and I can tell you many stories about the cell processor. The cell processor was from IBM. Okay, so it's a processor from IBM. And the idea of this processor, if I don't remember bad, is that it has 1 or 2 cores. I don't remember how many. I believe it was one processor that was a complete processor with all the packets, okay, able to execute any kind of task. And then it had like an array of 4, if I don't remember bad, simpler vector processing units. So if you wanted to execute cron, or, well, at that time, the cron didn't exist. If you wanted to execute a program, a normal program, you were going to execute it in the core, okay, in the main core. But whenever you wanted to do some linear algebra, something that was computationally very heavy, you could implement it using these smaller processors. Okay, so the cell processor was the processor that equipped the PlayStation 3. Okay, the PlayStation 3 was made of cell processor, and actually we bought some of them, some PlayStation 3, because we wanted to make some research about programming this processor, and we bought PlayStation 3 for the lab. Okay, and we didn't play with the PlayStation. No, it's true, we didn't play. We just programmed the cell processor. Okay, and the Mare Nostrum, the first version of the Mare Nostrum is the biggest supercomputer in Spain and one of the biggest supercomputers in Europe, that is in the Barcelona Supercomputing Center. Actually, if you visit Barcelona sometime and you are interested in HPC, you should organize a visit to Mare Nostrum, because the supercomputer is in a church. Okay, it's installed inside a church, former Catholic church or something like that. And then if you go there, it's you can search for pictures in the internet. You Google Mare Nostrum supercomputer, and you will see a supercomputer inside a church. Okay, and it's a very nice facility. So the first version of Mare Nostrum was composed of cell computers, so cell processors, sorry. And the cell architecture was a complete failure, okay? I don't know if it was too early for this kind of architectures, but the main problem of this is that for the PlayStation 3, it worked well because most of the game developers just use the same engine, or they have heavily optimized engine, and then somebody makes the programming of the engine, and the others just interact with some interface. But if you wanted to program something in Mare Nostrum, the people that worked there said that this was a nightmare to program, okay? Because, for instance, every time you have to do things in these processing elements, you have to send the data explicitly to that part of the computer. So, in practice, was as bad as programming a GPU, okay? But applied to a supercomputer and to every node of the supercomputer, and probably this happened too early for this kind of approach. So, at the end, we have three approaches. Fewer cores, but more complex is one of them. This is the most popular one. Simpler cores, which allows to put more cores in the same chip, and heterogeneity, that is always the future, okay, but it never comes to the desktop computers. And the idea is that we are going to have like different kinds of cores, some simpler and some more complex, dedicated to different tasks. Okay. Regarding the memory interface, as you can imagine, for instance, the processors that I have in my desktop computer have 12 cores. If they are running things at the same time and they are generating memory access, obviously this is putting lots of pressure on memory. So you have to find ways to make this effective in the chip. And one solution for this is stacking the memory chips on top of the processor chips and spreading this way the connections on the area of the chips. Something that you can check in Wikichip, in the website, is the different cache organization, okay? So normally, when you have a multi-core computer, you are going to have like different levels of cache, normally 3, okay? But in mobile processors, sometimes you have just 2. And normally, the last level cache, actually this is the name that receives whenever it's level 2 or level 3, depending on the situation. This is usually shared among all the cores, okay? And the above levels are private to each core, okay? And this is like a heuristic, okay? Every architecture is like this. Okay, so this is a first approach. So everything is private to each core. I have a core with its own level 1 cache and its own level 2 cache. And there is nothing shared among the cores. This was very popular in the first multi-core processors of AMD. The AMD Athlon X2 was one of them. okay? Actually, I had one. And at that point, the difference between the caches in AMD and Intel was that in AMD, every cache level was private to each core, while in the Intel processor, that was the rival of the Athlon, were the Core 2 Duo, okay, or Core Duo. And in this case, you can see that it's different. Here, everything is private to each core, and this was actually the future, okay? We have level 1 private to each core and a shared level 2. Remember that always the last level is called the last level cache and is usually shared among all the cores. Sometimes we have a mixture of the previous situation, like in this architecture, Intel Hoppertown. For instance, here we have 8 cores. All of them have private level 1 caches, and the level 2 is shared, but between pairs of cores. Okay? This happens sometimes in computer architecture, but is not very common anymore. Okay? And the most common architecture right now, like Intel NetHalling, okay, is that I have like two sets of 4 cores. Each core have a level 1 and a level 2 private cache, and each group of 4 cores have a level 3 shared cache. Okay, and this is the most usual organization, and I believe that if you check any of the 3 state-of-the-art architectures that I linked to you, probably all of them follow this layout. Okay. Okay, and this is Dunnington. Okay, this is twisted. Okay, so the first level is private to each core. The level 2 is sharing pairs, and the level 3 is sharing groups of 6. Okay, so you have like different options, and obviously they come up with this idea. They implement it in simulators, and if they are successful, they implement it finally in hardware. Okay, how to connect? We talked already about this. At the beginning of the multi-core area, they wanted to shorten time to market. They started with designs that were single core, and they found the best approach to do it fast without redesigning the whole processor. And this was the off-chip bus connection. Okay, the connection happened outside of the bus or in a low level of the hierarchy. But nowadays, the most popular approach is to connect in one of the shared levels of the cache. Okay, so this is just a discussion about different interconnection. This is nothing related to multi-core processors. This only says that there is a type of connection or network which is on-chip networks that are used to interconnect different components of a chip, of the processor. And in this case, we are connecting different cores. Okay, this is the interconnection, this one, of Niagara. Okay, so you can see that the level 2 cache is split in different banks, and all of them are interconnected using a crossbar interconnection. Okay, that is like an all-to-all connection. This is a possibility, and the other is the one in the cell processor. Okay, this is the one that I mentioned before. Okay, these are the small processors that I mentioned before, and this is the bigger processor. Okay, that is the main computing unit. And here the interconnection is a ring, okay? So you can imagine how it works, okay? Everything is connected to a ring that is like a shared interconnection system. Okay, and that's it. Any questions about this? No. Okay, so it's Friday, 7-11. It's time to have a rest from this long week. I'm not going to teach this subject any other day. Okay, so goodbye from this subject. But next week I'm going to be your teacher Tuesday and Thursday in HPC tools instead of Emilio. Okay, so see you on Tuesday. Somebody asked what kind of connection is used by AMD between CCAs on last generation. I don't know, probably a ring, but I don't know. I should check the documentation. Okay. Okay, so any comments from Teams?
Sí, Diego, yo tenía una pregunta. Para el trabajo lo podemos entregar en español, me imagino.
Sí, sí que podéis.
Vale.
You can handle the task in Spanish and in English, but not in French, sorry. Sí, en español sí.
Perfecto, muchas gracias.
Vale. Okay, so see you on Tuesday, those of you that have HPC tools.
Gracias, hasta luego.
Hasta luego.